Hello all, in this lesson we're going to be studying metallic bonding, which is something a lot of you have already been asked about. It does involve the bonding of more than one metal atom, but it still is going to be based on the concept of valence fulfillment, and it has some extra properties that come with it, which you're probably already familiar with, which are conductivity, malleability, and ductility. There's a homework associated with this lesson. It's questions 38 to 44 on page 111. We'll do that in class when I see you. There's also a quiz associated with this lesson, so be prepared for that. And our aim is, why do metals act like metals? I want you to copy the same on your second piece of paper, classwork, and follow it with this chart and these 5 Lewis dot structures for molecules. I have some requirements for the activity when you get to class, but you don't need to follow these instructions yet. All right, metallic bonding. Metallic bonding is quite simply what happens when more than one metal atom bonds to itself or to each other. The one thing on which bonding depends is valence fulfillment. But valence fulfillment itself is really tricky in metals because metallic atoms being on the left-hand side of the periodic table and being in groups with low values, you can see that they only have 1, 2, or 3 valence electrons each. So if there was nothing else around but metals, what would metals have to do in order to complete their valence shells? If you were to think that perhaps the answer would be to transfer electrons to one or another, you would be incorrect. And the reason is because imagine that one metal were to transfer one of its 3 electrons to another atom. Then one atom would have lost an electron and would have 2, and the other would gain an electron and would have no more than 4. In that case, neither element is satisfied. So metals do not use transfer in order to fulfill their valence shells, and therefore would not have ionic bonds with each other. Imagine then that metal atoms would share electrons. Even if that were the case, covalent bonding happens when elements share as many electrons as they need. So let's say they need to have 1 more electron, so they'll share 1. But when you look at these metallic atoms, they only have 1, 2, or 3 electrons. So let's say that it had 3 electrons. It needs 5. It can't share 5 electrons because it only has 3 in its valence shell. And then that problem is worse the lower the number of electrons in the valence shell becomes. So metals also don't use covalent bonding in order to fulfill valence shells. In fact, they do something that is unique to only metallic bonding, and it's called a mobile sea of electrons. So mobile is, you probably know the word from mobile phones, but it just means that they move around. Sea as in a sea or an ocean, and of course electrons. So it's a large group of electrons that are all in motion. Instead of 1 or 2 atoms bonding together and sharing electrons, it's millions, billions, zillions of atoms that are sharing electrons with each other. So what they do is I like to think of it as a giant game of hot potato, and each of the atoms tosses their electrons up into the air, and they all, as a very large group, gain access to the entire sea of electrons. And in so doing, they reach a more stable state, and therefore they have fulfilled their valence in one way or another. So this animation, it won't move in this video. I apologize for that. But what the red dots represent in this animation these are the electrons that each of these metal atoms has tossed up in the air, and all of these electrons would just zip around the entire array of atoms. The gray circles represent the nucleus of each of the atoms, But they also represent any of the electrons the atom has which are not in the valence shell. So if I were going to condense that thought, I might say that it is the nucleus plus all of the non-valence electrons. And that is actually a term that we should know, and it's referred to as kernel. Should you see the animation, the electrons would be behaving in in a very odd way. They would be zipping from one atom to the next throughout the entire array. And the reason they're doing this is that this is the most stable state for all the atoms in the array. And also this leads to one of the properties that you already know for metallics, which is that they are conductive of heat and electricity. So electricity is actually just a flow of electrons. And electricity would flow very easily through metals because since they have their mobile sea of electrons, they would actually provide no resistance to a river of current that would run through. You may remember from a very recent lecture that ionic substances, when they have been melted or dissolved, also have the ability to conduct electricity because the charges have become mobile in that substance, and this is the exact same concept as the mobile sea of electrons. So electricity will always flow whenever you have mobile charges. You probably also know that metals are very, very strong substances for the most part, and this is because since they all share a valence shell to achieve their most stable state, then moving away from one another would be choosing an unstable state. And you guys already know that elements want to be stable. So therefore, metal atoms and the bonds they form with one another are actually considered relatively difficult to break as a result of the elements having to become unstable before moving apart. Therefore, since atoms want to stay near each other to keep their stability, they will actually have very high melting points compared to other types of substances. All right, I'm going to try to explain malleability and ductility to you. Metals can be pounded into a sheet or pulled into a wire. Those properties are, in order, malleability and ductility. And the easiest way to understand this is basically that metal atoms are very easily able to slide past one another without causing fractures. I'm purposely contrasting this with ionic substances, which fracture easily when struck. And that's because of the alignment between positive positive and negative negative ions when ionic substances are struck. But since metal atoms are doing this ultimate game of hot potato and they're creating a mobile sea of electrons, you actually don't have any ions within the metallically bonded substance. All the kernels will have the same charge, and they'll all be, which is positive, and they'll all be swimming in a mobile sea of electrons. Therefore, there are no positive positives to line up with one another, and there are no negative negatives to line up, and you will not see any fracturing when metals are struck. Instead, in fact, you see metals dent when you strike them, which is really a really interesting property for a metallic substance. And the diagram below, right here, shows you that in a before and after. So we have the kernels, which are all swimming in their mobile sea of electrons. And if you were to strike a metal, like with a tin punch, you would be able to move many of the atoms in the top layer, and they would push the atoms below them down, causing the dent. But unlike an ionic substance, the mobile sea of electrons can travel with the kernels, and you will not get any alignment of like charges, and therefore you won't get a fracture as well. Therefore, metal atoms will remain bonded together even when forced out of shape. So here's your pair up. Please do copy down the diagram and the questions. but please don't answer the questions. I would like to do that together in class. And here are your summary questions, all of which I think are pointed and important. So please write down these questions without answering them, and we will answer them in class. Thanks for watching.